This is a problem involving an open steady system, a steam turbine in this case. We are given the inlet and exit state, information on that, and we are asked to find the shaft power, entropy generation rate in the turbine's universe, and the isentropic efficiency of the turbine. Because we have to find the isentropic efficiency, from the very beginning we'll think that the exit state, we'll think of two different states. One is exit state 2, the ideal exit state, and 3, the actual exit state. So 1 to 2 would be an ideal turbine, and 1 to 3 is the actual turbine. So let's solve the problem of the actual turbine first. So we write down what is given on state 1. Before that, let's get the governing equation down for the shaft power. The energy equation is simply dE dt single inlet. So I'm applying it between state 1 and 3. And it's an adiabatic turbine, so Q dot goes to 0. It's a steady state. So therefore, the shaft power or the external work transfer is given by m dot J1 minus J3. And because we are neglecting any KE and PE changes, we can write this as m dot H1 minus H3. So therefore, we need to find H1 and H3 to find the turbine output. We'll come back to the entropy analysis later. So we go on and find what is known at state 1, and from there the pressure is given 6 million pascal, temperature is 500 degrees Celsius, and the mass flow rate is 5 kg per second. Well, so we are to find this particular state. In other words, we'd like to know what is enthalpy and probably what is entropy. So we draw a TS diagram. First thing, to make sure we know where the state belongs. At 6 MPa, suppose this is the 6 MPa line, constant pressure line on a TS diagram. State 1, we know probably is a superheated state, but to prove that, we find the saturation temperature T set at 6 MPa. T set at 6 MPa equals how much? And to do so, we go to test property tables. H2O pressure saturation table will give us T set at 6.6 million pascal. So we go to 6 million pascal, which is right about here. And as you can see, the temperature is 275 degrees Celsius at 6 MPa. So we go back and realize that this temperature is about 276 degrees Celsius. And the given temperature is 500 degrees, which is way up here. So that must be our, our state. Let me draw it a little bit differently. Let's say this is our state. Okay, so state 1, to find enthalpy and entropy, we go to the superheated table now, because we have determined the state 1 is superheated. So we start the superheated table and go to 6 MPa, which is way down here. Oh, there is no 6. There is a 6 MPa line and 500 degrees Celsius. So you can see that this is the property line. We don't need an interpolation here. At 500 degrees Celsius, we can pick up enthalpy to be 3422 and entropy to be about 6.88. So I'll write those numbers down. So enthalpy is 3422 and entropy is 6.88. We'll not put down the units here because these are standard SI units. What about state 2 now? State 2, pressure is way low, 4.5 kPa, and also it's given, let's see what's given with state 2. I'm sorry, state 3. At the exit, the pressure is this. And the quality is given. This is not correct. Let me correct the problem a little bit. And the solution I have is that the pressure is this, and sorry, the temperature is not given, and it is, and quality is 100%. In other words, is saturated vapor. That's what is given. I'm sorry. This should have been the statement of the problem. I have the corresponding solution. If the temperature is given, this problem will be slightly different. But let's stick on with 4.5 kPa and saturated vapor. In that case, the exit state will be somewhere, as you can see, right here. That will be our state 3. So state 3 would be relatively straightforward then to find. Pressure is known and X is known. Therefore, enthalpy, entropy, and entropy can be found from, if we can go back to the saturation table. So we go to the pressure saturation table, find 4.5 kPa, which is between 4 and 5. So as you can see, we can pick up enthalpy from here in between 4 and 5. So this is our average of these two, and the entropy will be the average of these two. So we'll just eyeball it, and instead of spending a lot of time trying to interpolate. So if we eyeball in between, what we get is enthalpy to be, let's say, 2.558 and entropy to be 8.43. So now that we have enthalpies in both states, we can very easily calculate the external work, which is the same as shaft work because there is no boundary, or electrical work is given by mass flow rate and the enthalpy difference. (4320 kilowatt). That's the formula, m dot times H3 minus H1, right? That's what we calculated. So therefore, the shaft work is found. We'll come and verify that in a second. Let's first figure out the entropy generation. ds dt will be m dot S1 minus m dot S3 q dot over TB plus S dot gen of universe. What we say by universe, what we mean is that we draw a boundary which encompasses more than just the turbine. The boundary passes along the immediate surrounding, so that we have captured all entropy generations. If it is internal entropy generation, then the boundary will be fitting just the H2O inside. Okay, with that in mind, we go and analyze, and we recognize that steady state, this term goes away, but it's adiabatic. So it doesn't really matter where the boundary exactly passes, because there is no entropy generation due to heat transfer. So therefore, the entropy generation rate turns out to be simply m dot S3 minus S1, which is 5, and S3 and S1 have been already calculated. I'm just substituting that, and that gives us the answer of 7.75 kilowatt per Kelvin. So therefore, we have found the entropy generation rate, and we have found the external work from this turbine. Now to find the isentropic efficiency, we have to go back and ask ourselves, if this is the actual turbine which goes from state 1 to state 3, how will the ideal turbine will be what? 1 and 2. This will be our state 2, where the entropy remains constant, right? An ideal turbine will have isentropic exit, no heat transfer, and no friction, will produce entropy to be constant. So for the ideal turbine, if we can find out the exit state 2, then we can calculate the ideal output. So therefore, let's try to find state 2, where we know pressure is given, same as state 3, and we know S equals S1, which is entropy at 1 was 6.88. We already found it. So if you know, look, we cannot assume that the state is where the state is. We just know that the pressure is 4.5 kPa, and we know the entropy of the state to be 6.88. But we cannot say if the state 2 is inside or outside the dome. So what we need to do is to find the F and G property first. So what is SF at 4.5 kPa? And what is SG at 4.5 kPa? This is the manual way of solving the problem. So we go back to the, again, we'll go back here and find the 4.5 kPa, which is somewhere between these two lines. And we can pick up what is SF and SG, which will be in between these two values. And also we can at the same time pick up what is HF and SG, H and G, I'm sorry, in between the two. HF and SG at 4.5 kPa. If we interpolate between these two rows, and we can pick up these numbers as, and I have written them down, SF would be approximately 0.45. You can go back and check, and it would be 8.42. Now we know that S is supposed to be 6.88, which is in between this two value. So therefore, we must have state 2 might be somewhere here, which is a mixture. Given that, we can quickly write, therefore, what it means, S must be equals 1 minus X times SF plus X times SG. And we know all these values. S is 6.88, 1 minus X times SF, which is 0.45, plus X times 8.42. If you just do your algebra right here, you can show that X will turn out to be 0.806. Let's say approximately 0.81. So we found the quality of the exits at the ideal exit state. So therefore we can find enthalpy would be 1 minus X HF at 4.5 plus X times G at 4.5 kPa. And you can show that, again, going back to the table, we can 0.81, H can be shown to be about 130, 0.81 times 2557, and this will give us an enthalpy of 2096. Now that we know the enthalpies at state 1 and 2, we can show that the external work for the ideal turbine is m dot H1 minus H2, and we got all the numbers here. 5 times H1 we already found, and H2 we just found, and that gives us 6030 kilowatt. So the isentropic efficiency, or the turbine efficiency, is what? W dot external actual turbine, or divided by W dot external ideal turbine. In this case, it will be H1 minus actual is 3, ideal is 2. And actually we found the work, so we can directly put, we don't need to put enthalpy again because we already found the actual work and ideal work, and that gives us 64.5%, I think about 65%. So we got a 65% as an isentropic efficiency, and we answered almost all part of these questions. Now let's go and verify this answer using a TESTcalc. Okay, so I guess we have to log in again. And we'll launch open generic single flow system PC model. And you can see the line, I mean, this is the hierarchical path name, how we arrived here. And we say run. Okay, H2O is already the default fluid, so we don't have to bother worry about that. And let's start entering what we know about the problem. State 1, what we knew are 6 MPa, 500 degrees Celsius, and mass flow rate of 5 kg per second. And that gives us enthalpy and entropy, which we can verify to be correct, what we got manually. Let's go to state 2 is the ideal state. So we know ideal state is we have a 4.5 kPa. Remember, ideal state and actual state, the pressure must be the same because the turbine is designed for that. And entropy is equal entropy at 1. Of course, there is no change in the mass flow rate. So let's specify that. So state 2 has been calculated. And state 3, we can write P2, 4.5 kPa, and it was a saturated vapor, if you recall, the actual exit state. So that gives us all the different states completely evaluated. We can check that, how good the calculations are in the TS diagram. If you do constant pressure lines, then you can see that from 1 to 2, it's like a constant, from 1 to 2 is isentropic, and from 1 to 2 is an isentropic line, and 1 to 3 you can see entropy has increased. It's an actual turbine line. Okay, so let's go, and now that we found the states, go to the device panel, evaluate the actual state, actual device. 1, 2, 3 is our actual device. There is no heat transfer, and if I hit enter, it calculates the work or the power 4320, and the entropy generation 7.76. What we got are very close. What we got were 7.75, as you can see here, and our work was 4320 external work for the actual turbine, and this is exactly almost exactly what we got. The entropy generation rate is given here. Okay, if we want to find the isentropic efficiency, let's find the ideal turbine. Let's call turbine B as the ideal turbine, going from state 1 to state 2. Notice that when I select the states 1, 2, the diagram reflects the selection. Heat transfer is 0, and you can just do a calculate here and find the actual work. This is the ideal work, 6682, and I believe what we found before was 6630. Again, very close. So therefore, to find the isentropic efficiency, we could just divide the two work, or we could use the formula for the isentropic efficiency. Either way, we'll get the same answer. So H1 minus H3 divided by H1 minus H2. These are enthalpy differences proportional to work output of the actual and ideal turbine, and that produces an efficiency of 64.5%. 64.65%. What we got was 65%, so pretty close, 64.65 and 65. So I'd say this is a pretty good answer. It's getting too long, so I better stop here, and I hope you can go over this solution thoroughly and solve similar problems to have a complete understanding of how to analyze open steady devices involving a PC model.